Hello everyone. My name is Sonu and I am the student of BSc Chemistry Honours second year from Pandit Nekiram Sharma Government College, Rohtak. Today we will read the chapter of the thermodynamics second for visually impaired students. So the first law of thermodynamics had certain serious limitations. To overcome these limitations, a strong needs was therefore felt to introduce another law called second law of thermodynamics. A few limitations of the first law and a consequences some definition given to second law are briefly given below. A major limitation of the first law of thermodynamics is that it merely indicate that in any process there is an exact equivalence between the various forms of energy involved, but it provides no information concerning the feasibility of the process, whether the process is possible or not. For example, the first law does not indicate whether heat can flow from a cold end to hot end or not. All that it tells is that if the process occurred, heat energy gained by one end would be exactly equal to the lost by the other end. Similarly, the first law does not tell whether a gas can diffuse from low pressure to high pressure or water can itself run uphill, etc. The second law supplies answer to above question by starting that all spontaneous processes like the flow of heat from the hot end to cold end, diffuse of a gas from high pressure to low pressure, or the flow of water downhill, etc., are thermodynamic irreversible. The term spontaneous process used in the above definition means a process which can take place without the help of external energy or natural processes, some of which is mentioned in the definition above the spontaneous process. However, it may be mentioned there that the spontaneous does not give any idea of the rate of process, whether the process takes place fast or slowly. All that it implies is that a process can occur without the help of external energy. The first law states that when heat is converted into work, the work obtained is equivalent to the heat absorbed. However, it has been seen from experience that the heat absorbed cannot be completely converted into work without leaving some change in the system or the surrounding. The complete conversion of heat into work is impossible without leaving some effect of elsewhere. Is that is second definition. Beside the above definition, a number of other definitions have been also been given to the second law of thermodynamics, which is it is impossible to construct a machine functioning in cycle which can convert heat completely into the equivalent amount of work without producing some change elsewhere, which is third definition. And without the use of external agency, cannot with itself pass from a colder to hotter body. It is fourth definition. The term functioning in cycle is introduced in the above definition to indicate that the machine must return to its original state at regular intervals so that the function continuously. Further, it may be recalled that an isothermal reversible expansion for an ideal gas in which del U is equal to 0, so that Q is equal to W, is that the work done is exactly equal to the heat absorbed by the system. In other words, in this process, heat is completely converted into work. However, it is important to observe that the conversion of accommodated by an increase in volume of the gas so that the system has undergone a change. A number of other definitions have also been given to the second law of thermodynamics, which will come across in the section of the chapter. The fraction of heat absorbed by a machine that it can transform into work is called efficiency of the machine. N is equal to W by Q. The machine used for conversion of heat into work is called heat engine. In order to bring about this conversion, the engine absorbed heat from a heat receiver at high temperature called source, converts a part of it into work, and return the remainder to receiver at a lower temperature called the sink. Now, the main important topic is Carnot cycle and its efficiency. A cycle is a process in which a system returns to its original state after a number of successive changes. A process conducted in the manner is called cyclic process. The engine chosen by Carnot, called Carnot engine for the purpose for the calculation of efficiency, was a hypothetical one and cannot be achieved actual practice. It was selected because it could be subjected to simple thermodynamic treatment. It consists of a cylinder containing 1 mole of ideal gas as the working substance and fitted with a weightless, frictionless piston so that all operation in the cycle is carried out reversibly. For this reason, it is also called reversible heat engine. The cylinder is supposed to be insulated on all sides except at the bottom so that heat can flow to form the system only through the bottom. Further, it is supposed that there are two heat receivers, one at a higher temperature T2 called the source and other at a low temperature T1 called the sink. Some operation is carried out by placing the cylinder into the process isothermal. On the other hand, if during an operation the cylinder is placed on the insulating material, no heat exchange can take place between the system and the surrounding and hence process is adiabatic. The Carnot cycle consists of four different operations which can be represented on pressure volume diagram, sometimes called an indicator diagram. These operations are carried out in next section. First is isothermal expansion. The cylinder containing 1 mole of ideal gas occupying a volume V1 is placed in contact with the source. The gas absorbs heat Q2 from the source and expands isothermally and reversibly till the volume increases to V2. The path of the process is represented by the isothermal curve AB. Since the gas is ideal, so the work done W1 of 1 mole of ideal gas will be minus W1 equal to RT2 ln of V2 by V1, and work done is equal to the heat minus W1 is equal to Q2 is equal to RT2 ln of V2 by V1. Second step is adiabatic expansion. The cylinder is now removed from the source and placed in perfectly insulating material so that the gas now expands adiabatically and reversibly. Work is done in the expansion, but since no heat enter or leave in the system, temperature must fall. Reversible adiabatic expansion is continued till the temperature has fallen to T1, which is temperature of the sink. Suppose the corresponding volume become V3. The path shown by the adiabatic curve is BC. So the work done minus W2 is equal to CV T2 minus C1 and then is minus CV T2 minus T1. And third is isothermal compression. The cylinder is now removed from the insulating material and placed in the contact with the sink. The gas is compressed isothermally and reversibly till the volume decreases from V3 to V4. The process is represented by the path CD. The work done in this will be positive. So W3 is equal to RT1 ln of V4 by V3. During this operation, the amount of heat will be minus Q1 is equal to W3 will be equal to the RT1 ln of V4 by V3. Adiabatic compression. The cylinder is now removed from the sink and placed again on the insulating material. The gas can be compressed adiabatically and reversibly along dA till the initial state A is regained. The temperature of the gas rises from T1 to T2. The work done is positive, and so the W4 will be equal to the C1 T2 minus T1. As a result, these four operations, the system has returned to its original state. So it is a reversible cycle, and the net work done will be equal to the minus W1 minus W2 plus W3 plus W4. So the total work done will be RT2 ln V2 by V1 plus RT1 ln of V4 by V3. Since V1 and V4 lie on the one adiabatic curve and V3 and V2 lie on the another adiabatic curve, so V4 by V1 both raised power gamma minus 1 is equal to T2 by T1 and V3 by V2 both raised to power gamma minus 1 is equal to T2 by T1. Comparing both equation, V4 by V3 is equal to V1 by V2. Putting in this value, RT2 ln of V2 by V1 plus RT1 ln of V1 by V2 is equal to RT2 ln of V2 by V1 minus RT1 ln of V2 by V1. So taking R common, RT2 minus T1 ln of V2 by V1. Dividing equation 12 by equation 2. So W by Q2 is equal to T2 minus T1 by T2 gives the efficiency of Carnot cycle or engine. And next is Carnot theorem. It is clear the efficiency of reversible heat engine depend only upon the temperature of the source and the sink and the independent of the nature of the working substance. Another important observation is made from the above observation is that the work done in the cycle is only one involved in the isothermal operation because the work done in the adiabatic operation cancel one each other. Further discussed earlier, work done in reversible isothermal expansion from A to B is maximum where the work done on the gas during reversible isothermal compression from C to D is minimum and the total work done by the system is maximum for the specific condition and therefore efficiency is maximum. The result that follows from the Carnot cycle will be efficiency of reversible heat engine depend only upon the temperature of source and the sink and independent of the nature of working substance. In other words, all reversible heat engine working between the same two temperature have the same efficiency. Further, it said that the efficiency of reversible heat engine is maximum for the given temperature. Since the quantity T2 minus T1 by T2 is always less than unity, so the efficiency of heat engine is always less than unity. It heat engine absorb a certain amount of heat from the source, convert a part of it into work, and return the rest into sink. In other words, it is impossible to convert heat completely into work. So the efficiency N is equal to W by Q2 is equal to Q2 minus Q1 by Q2 is equal to T2 minus T1 upon T2. Next topic is concept of entropy. Entropy is a state function. For a reversible Carnot cycle working between temperature T2 and T1, it has been seen that Q2 minus Q1 upon Q2 is equal to T2 minus T1 upon T2. The above equation can be simplified as Q2 by T2 is equal to Q1 by T1. We conclude that heat absorbed or lost isothermally and reversibly divided by the absolute temperature at which the heat is absorbed or lost is constant quantity for a particular system. From the equation second, Q2 is the heat absorbed at the temperature T2 and Q1 is the heat lost at temperature T1. If Q1 were the heat absorbed at temperature T1, so the equation becomes Q2 by T2 is equal to minus of Q1 by T1 or Q2 by T2 plus Q1 by T1 is equal to 0. So the summation of Q by T is also equal to 0. Hence the for an infinite number of Carnot cycle, summation of del Q upon T will be equal to 0. It implies that the total value of quantity of Q by T for a path A to B is equal to the total value of quantity Q by T for the reverse path of B to A. Hence, it may be concluded that the quantity Q by T is a state function. Its value depends only upon the initial state and the final state. It is independent of the path. Obviously, Q by T is the change in the value of quantity of a function having some definite value of A and B. Depending upon the value of quantity, pressure, volume, and temperature, this quantity or function is all called entropy and is usually represented by the symbol S. So the Q by T is equal to Sp minus S1 which is equal to the del S which is entropy, change in entropy. As entropy may be defined as a state function, the change in the value of which from the initial state to the final state equal to the quantity of Q by T is that the total heat absorbed reversibly and isothermally in going from the initial state to the final state divided by the absolute temperature at which the heat is absorbed. The entropy change may be also defined directly as the quantity of heat absorbed isothermally and reversibly divided by the absolute temperature at which the heat is absorbed. It is important to note that entropy is a state function. Therefore, the value of entropy change during a process should not depend upon the path, whether the heat is absorbed reversibly or irreversibly during the process. However, since the derivation of the above result is based upon the Carnot cycle in which heat is absorbed reversibly, therefore expression for the entropy change is valid only when the heat is absorbed reversibly. It is better to use the symbol Q reversibly in the place of Q. So the expression may be also used as delta S is equal to the Q reversibly by T. Unit of entropy from the expression del S equal to Q by T. It's obvious that unit of entropy will be calorie per degree. Heat is expressed in calorie. Further, entropy is extensive property. It is therefore important to mention quantity of substance involved. It is usually expressed for 1 mole of substance. Hence, the entropy unit are calorie per degree per mole. If heat is measured in joule, the unit of entropy will be joule per degree per mole. Entropy change in reversible process. Suppose a process occur under completely reversible condition. It is the heat is absorbed by the system reversibly and the heat is lost by the surrounding also reversibly. If Q reversibly is the heat absorbed by the system, then the heat loss of surrounding will also be Q reversibly. If the process takes place isothermally at the absolute temperature, then entropy change of system will be delta S of system will be equal to Q reversibly upon T, and the entropy change of the surrounding will be delta S of surrounding is equal to the minus of Q reversibly upon T. So the total entropy change will be equal to the delta S of system plus delta S of surrounding will be equal to the Q of reversibly upon T minus Q of reversibly upon T. Both of they cancel each other and the total entropy of the system and surrounding will be equal to 0. It may be concluded that in reversible process the net entropy change for the combined system and the surrounding is 0. Is that there is no net change in the entropy. Entropy change in irreversible process. If any part of process is irreversible, the process as a whole is irreversible. Suppose that a total heat lost by the surrounding is Q irreversible. The heat will absorbed by the system, but the entropy change the system does not depend upon the heat actually absorbed, but it depends upon the heat absorbed reversibly on the quantity Q reversible. Thus, if the heat is absorbed isothermally by the system at the absolute temperature T, the entropy change of the system will be delta S of system is equal to Q reversibly upon T. And the surrounding delta S of surrounding will be equal to minus of Q irreversible upon T. So total energy, total entropy change of combined system and the surrounding will be delta S of system plus delta S of surrounding will be equal to the Q of reversibly upon T minus Q of irreversible upon T. Now we know that work done in reversible process is maximum work. So the work done in reversible process is greater than work done in irreversible process. So that internal energy in the state function, the value of delta U same whether process is carried out reversibly or irreversibly. So the delta U is equal to Q reversibly minus W reversibly is equal to Q irreversibly minus W irreversibly. Combining both equations, Q reversibly upon T minus Q irreversible upon T greater than 0. Thus it may be concluded that in an irreversible process the entropy change for the combined system and the surrounding is greater than 0 and an irreversible process is accompanied by the net increase of entropy. All spontaneous processes are accompanied by the net increase of entropy. Next topic is Clausius inequality. As discussed above, in irreversible process, the result given is equation is delta S of system plus delta S of surrounding is greater than 0. So the delta S of system is greater than minus delta S of surrounding. So the delta we know that delta S of surrounding is equal to minus Q upon T. Putting in value delta S of system will be greater than Q by T. For small change, ds of system is greater than minus ds of surrounding. the ds of system is greater than dq by dt. These expressions are called Clausius inequality. For spontaneous expansion, irreversible adiabatic expansion surrounding, suppose the system undergo irreversible adiabatic change dq is equal to 0, hence the Clausius inequality ds of system is greater than 0, then the entropy of system has increased further as dq is equal to 0. It means that no heat is transferred into the surrounding, thus ds of surrounding is also 0. As total energy change, ds of total is equal to ds of system plus ds of surrounding is equal to ds of system, but delta s of system is greater than 0, hence delta s of total is also greater than 0. Irreversible isothermal expansion, we know that when a perfect gas expands isothermally, its internal energy remain constant is equal to delta u is equal to 0. Hence, according to first law of thermodynamics, du is equal to dq plus dw, or dq plus dw is equal to 0, or dq is equal to minus dw. If gas expands freely in vacuum, no work is done, so dw is equal to 0. Substituting this equation, spontaneous cooling. Suppose a heat transport from one system to higher temperature T2 called the source. Another system is low temperature T1 called sink. If heat Tq leaves the source, entropy change of source is equal to minus dq upon T2. Entropy change of sink is equal to dq by T1. Total entropy change ds total is equal to dq by T1 minus dq by T2. Taking dq common, dq is equal to dq 1 by T1 minus 1 by T2. Entropy change in the universe. Entropy of the universe is continuously increasing. This result is sometimes taken as another statement of the second law of thermodynamics. The energy of the universe is constant, where the entropy of the universe is continuously increasing and tends to the maximum. Thank you.